the motion of the vehicle along the curved road. For that, we have seen the maximum speed limit at the normal horizontal road surface. The formula was V is equal to square root of mu rg. That was our first derivation, where mu is called as the coefficient of static friction. Now, in that case, we have seen that we have the maximum speed depends on the friction, but the friction has the upper limit. Therefore, we can't increase the maximum speed limit. For that reason, the roads are banked. We have seen the next time the second derivation, that is the speed limit at the banked road surface. The speed limit at the banked road surface, that is V is equal to square root of Rg tan theta. V is equal to square root of Rg tan theta. Theta is called as the angle of banking. In this case, we have not considered the force of friction or the friction. We have derived only considering the angle of banking theta. V is equal to square root of Rg tan theta, that is the maximum speed limit at the banked road surface. From that, we can also derive the formula for the angle of banking, that is theta is equal to tan inverse of V square upon Rg. We are up to this point. Now the third derivation by considering the friction. Now in this case, we have derived the formula V is equal to square root of Rg tan theta, but the value of this V can be less than this root Rg tan theta or greater than the root Rg tan theta, which depends on the friction. Now the third derivation, that is the minimum possible speed limit, and the fourth derivation, that is the maximum possible speed limit. In the case of the minimum possible speed limit, let the speed v1 is less than the root Rg tan theta, that is the speed limit is less than the root Rg tan theta. In that derivation, we are going to see that v greater than the Rg tan theta. Now suppose this speed limit is called as the v1. v1 is root less than root Rg tan theta, that is m1 square upon r less than the n sin theta. That is in this case, the centripetal force is less, that is the centripetal force balances, the centrifugal force is less, the centrifugal force balances the centripetal force. Here we have taken v1 less than root Rg tan theta, where the force due to the friction is in the upward direction along the road surface. This is the direction of the force of friction Fs. Now here this force of friction Fs, we have seen this part, that is the normal reaction N is having the two components n cos theta and n sin theta. Drawing the N, this N is perpendicular to the road surface, and the N is perpendicular to the road surface, that can be drawn in this manner. This is perpendicular to the road surface. Now the N is having the two components n cos theta and n sin theta. Here the force of friction Fs are having two components, Fs cos theta and Fs sin theta, where Fs cos theta opposite to the n sin theta. This is the direction of n sin theta. This is the direction of Fs cos theta, which are in the opposite directions. Where the second component, this is the angle of banking theta. This is the angle of banking theta. This Fs sin theta is along the direction of the n cos theta. Fs sin theta is along the n cos theta. Therefore, the resultant force, that is mg, get balanced. These are the two forces, and therefore mg is equal to Fs sin theta plus n cos theta. That is the equation number 1. Now here n sin theta in this direction and Fs cos theta in this direction, the centripetal force is towards the center. Therefore, the centripetal force mv1 square upon r. Here we have taken the velocity as v1. mv1 square upon r is equal to n sin theta minus Fs cos theta. That is equation number 2. Now dividing 1 by 2 by the calculation, that is the solving the equations 1 by 1 and 2. we take the equation that is the of velocity, minimum velocity v1 is equal to root rg in the bracket tan theta minus mu s upon 1 plus mu s tan theta, and this is the value of the minimum possible velocity. Now in the book also this is given the direct equation v1 is equal to, we can solve these two equations. We found that v1 is equal to square root of rg in the bracket tan theta minus mu s upon 1 plus mu s tan theta. If in this case mu s greater than or equal to tan theta, mu s greater than or equal to tan theta, equal to tan theta means the velocity v1 is equal to 0. This is the derivation. If you take the friction in the upward direction, that is the velocity is the minimum v1, that is v less than rg root rg tan theta, that is taken as v1. We take the derivation as v1 is equal to root rg tan in the bracket tan theta minus mu s upon 1 plus mu s tan theta. Now in the second derivation, maximum possible speed limit, this is the minimum possible speed limit, that one is important for us because we want the maximum speed limit. In the case of the maximum speed limit, having the same diagram but the friction is in the downward direction, this is the direction of the force Fs. This force of friction are having two components. One is Fs sin theta. This Fs sin theta is along mg. Fs sin theta is along mg. Second is the Fs cos theta. This component, this angle of banking theta, this is the angle of banking theta. Fs cos theta is along n sin theta, that is toward the center. They are in the same direction. These are in the same direction, and therefore the resultant force mg is equal to this n cos theta minus fs sin theta, n cos theta minus fs sin theta, that is equation number 1. Now second, this supplies the necessary centripetal force which get balanced by the centrifugal force. In this case, this mv2 square upon r greater than n sin theta, that is centripetal force is here large or greater. Here the centrifugal force is less. Here the centrifugal force is greater. Here mv2 square upon r is equal to n sin theta plus fs cos theta, that is equation number 2. Now from the equation 1 and 2, that is the solving equation 1 and 2, we get the equation v2 max is equal to square root of rg in the bracket tan theta plus mu s upon 1 minus mu s tan theta. This is the equation for the maximum possible velocity at the banking of roads considering the force of friction. This is the minimum possible speed limit at the bank road surface considering the friction. Here the friction is in the upward direction, there is a friction in the downward direction. This is the minimum possible speed limit, that one is the maximum possible speed limit. Here also, if mu s is equal to cot theta, we know that cot theta is equal to 1 upon tan theta, that is 1 minus 1. 1 minus 1 is equal to 0. Therefore, this V max is equal to infinity. In that case, the maximum velocity is equal to infinity. In the second case, if mu s is equal to 1, and tan theta is equal to 45 degree, in that case this one is equal to 1 minus 1, that is equal to 0. There again V max is equal to infinity. That is the maximum possible velocity is possible when mu s is equal to cot theta or theta is equal to 45 degree, mu s is equal to 1. In that case we get the maximum possible velocity. Now if we observe these two equations, v1 is equal to root rg in the bracket tan theta minus mu s upon 1 plus mu s tan theta. The second equation root rg tan theta plus mu s upon 1 minus mu s tan theta. Here there is sign minus, there is a plus. Here there is sign plus, there is sign minus. That is, they are the same equation. There are only the interchanging of the signs also. Second, if for both the maximum and minimum, that is this equation and this equation, if there is no friction, that is mu s is equal to 0. If there is no mu, that is mu s is equal to 0, no friction. In that case, if we substitute here 0, here 0, here 0, here 0, we get the equation that is v is equal to square root of r g tan theta, which one is already derived by us. These are the four equations, that is the motion of the vehicle along the curve. We have seen that at the curve road, the vehicle performs the circular motion. For the circular motion, there is a need of the centripetal force, which get balanced by the centrifugal force. On the normal horizontal road surface, the centrifugal force is supplied by the force of friction. We have derived the equation for that, that is the maximum speed at the normal horizontal road surface, that is v is equal to square root of mu r g. Second, in the case of the banking of roads, what is the need of the banking of roads? Now here for the maximum speed, we have to depend on the force of friction, but the force of friction is having the upper limit, which we can't increase the force of friction over that limit. Also, by increasing the friction, the road surface becomes rough, which causes the wear and tear of the rubber tires. Also, in the rainy season, mu decreases. Therefore, we can't totally depend on the force of friction. Therefore, the roads are banked. From that, we have derived the second derivation. In that case, the road surface is kept tilted with the horizontal. The angle of inclination is called as the angle of banking. The outer edge is at higher level than the inner edge, which is called as the banking of roads. With the help of the banking of roads, the normal reaction is perpendicular to the road surface, which are having two components, n cos theta and n sin theta. N cos theta get balanced by the weight mg. N sin theta supply the necessary centripetal force, which get balanced by the centrifugal force. From the two equations, we derive the equation for the banking of road, that is v is equal to square root of r g tan theta, or theta is equal to tan inverse of v square upon rg. This is the maximum speed limit on the banked road surface, or theta, that is the angle of banking. In this case, we are not considering the force of friction. The third derivation, considering the force of friction, that is for the third and fourth. In the case of the third derivation, we get the minimum speed limit. In the 4, we get the maximum speed limit, where if suppose the speed limit v, in this case v is called as the v1. If v1 is less than root rg tan theta, that is m v1 square less than the n sin theta, where the centrifugal force is less. In that case, this force of friction is in the upward direction. This force of friction are having two components. This is f cos theta, that is near the angle f cos theta, which is opposite to the n sin theta. This is the fs sin theta, which is along the n cos theta. Therefore, we can write the equation mg is equal to fs sin theta plus fs sin theta plus n cos theta. M v1 square upon r is equal to n sin theta minus fs cos theta. Solving these two equations, now from the book there is a direct derivation. We take the direct formula for v1. v1 minimum, that is the velocity, minimum velocity is equal to root rg in the bracket tan theta minus mu s upon 1 plus mu s tan theta. If mu s greater than equal to tan theta, mu s equal to tan theta means tan theta minus tan theta means 0. That is the minimum velocity will be 0. This is the minimum. Therefore, that is equal to 0. That one is the maximum. That should be equal to infinity. In this case, the maximum possible speed limit, we have taken the friction in the downward direction. For that, v2 greater than rg tan theta. V1 less than Rg tan theta, V2 greater than Rg tan theta. Friction is in the downward direction. This is the angle of banking. The component near the angle, that is Fs cos theta. This is Fs sin theta. Now Fs cos theta is along the n sin theta. Fs sin theta is along mg. Therefore, we can take the two equations. Mg is equal to n cos theta minus Fs sin theta. N cos theta minus Fs sin theta. Equation number 1. Then the centripetal force along the center mv2 square upon r is equal to n sin theta plus fs cos theta. Equation number 2. Solving the equation number 1 and 2, we get v2 max is equal to square root of rg in the bracket tan theta plus mu s 1 minus mu s tan theta. Remember these equations as this is minus plus, this is plus minus. Here we want the maximum velocity that should be up to infinity, and therefore mu s is equal to cot theta. Then this one is product of the cot into tan means 1 minus 1 is equal to 0. V max is equal to infinity. Second, if mu s is equal to 1, tan is equal to 45 means 1. This is 1 minus 1 means 0. Again v2 v max is equal to infinity. Here infinity, in that case 0. Now for both the maximum and minima, if mu s is equal to 0, if there is no friction, that is mu s is equal to 0, no friction, mu s is equal to 0, mu s is equal to 0, mu s 0, mu s 0, we get the original equation. V is equal to square root of r g tan theta. These are the 4 derivations for the vehicle having the turn or motion of the vehicle along the turn. So the equations, according to the equations, how is the example, from that we can solve the equations or the examples. Thank you.